Welcome back to Maths in an Empty Classroom with me, Mr. Southern. This is part 2 of the lesson on implicit differentiation, and in this video I'm just going to be going through a second example with some more complicated differentiation in there. So here I have, find an expression for dy dx given that x squared plus 5y squared minus 3xy equals 12x minus 7. And we're looking at the bit that's different about this to the previous example. It is that here I have this negative 3xy term, which is a product of x and y, and I'm just going to have to think carefully about how I'm going to differentiate that. The key thing is I called it a product, and therefore what we're going to have to do with this is to crack out the product rule. So what I'm going to do is I'm just going to begin by simply differentiating the term 3xy, and then we'll look at how to incorporate that within the rest of the expression. So what I'm going to do, product rule, I'm going to call 3xu and I'm going to call y v. And then I'm going to differentiate each bit. If u is 3x, then du dx is going to be 3. And if v is y, then dv dx is going to be dy dx. So if I'm then using the product rule, which is v du dx plus u dv dx, then I'm going to get my expression for the derivative of this to be v times du dx, that's 3y, plus u dv dx, which is 3x dy dx. So that there has just differentiated the 3xy part of this expression. So what I'm now going to do is I'm just going to rewrite the original expression and differentiate it a term at a time, incorporating that product rule. So x squared plus 5y squared minus 3xy equals 12x minus 7. Okay, so differentiating a term at a time. X squared will differentiate to 2x. 5y squared will differentiate to 10y dy dx. Minus, now we've established that this 3xy term will differentiate to this. So I'm going to put that in a bracket, 3y plus 3x dy dx. And it's important that I use that bracket because I'm subtracting both terms of this, and I'll deal with that in a moment. Looking at the right hand side then, if you differentiate 12x in terms of x, it's just 12. And differentiating negative 7 is 0, as when we differentiate constants. So let's just tidy this up a little bit then. We've got 2x plus 10y dy dx minus 3y minus 3x dy dx equals 12. And as with the previous example, I've been asked for an expression for dy dx, so I'm going to try now to write this with dy dx being the subject. So I'm going to keep the two terms that contain dy dx on the left hand side, so 10y dy dx minus 3x dy dx equals 12 minus 2x plus 3y, moving everything else over to the right hand side. This should be looking familiar now to you. Factorise out dy dx on the left hand side, which gives me 10y minus 3x inside my bracket. That is equal to 12 minus 2x plus 3y. And then finally, to get my expression for dy dx, I'm just going to divide by this bracket. So dy by dx equals 12 minus 2x plus 3y all over 10y minus 3x. So that is my completed expression for dy dx for this function, but the key point from this was that when your original function contains a product of both x terms and y terms, you have to use the product rule to differentiate that. Join me in the next video where I'll be looking at applications of implicit differentiation.